I'm Zoe Bentley, and welcome to Exogeology Rocks! Today we're going to hear from Professor of Astrophysics Geoff Marcy about the search for exoplanets, or planets which orbit around other stars.
Well, hello, my name is Geoff Marcy, and I'm a professor of astrophysics at the University of California at Berkeley, and I've been asked by Zoe for Exogeology Rocks to tell you a little bit about the research we're doing at UC Berkeley, especially the search for planets around other stars, indeed Earth-like planets around other stars, and also how we are searching for intelligent life in the universe. So I'm going to give you a little sense as to how we do this search. We're using some of the world's largest telescopes and indeed a Spaceborne Telescope. And the way we search for planets, even as small as that of the Earth, orbiting other stars, is by a very simple and new technique. We simply watch planets to see if they ever cross in front of stars, and when they cross in front of stars they'll block a little of the starlight, dimming the star. Distant stars with planets that are very small don't allow us to detect the planets directly, but we can see the dimming of the star as the planet crosses in front, a little like a bug landing on a light bulb. You would see the room dim. Here's how it works. We actually watch stars with our telescopes, and even though we can't see the planet in silhouette crossing in front of the star, we can measure the brightness of that star over the course of time, minutes, days, weeks, and see if the star dims for a while and then re-brightens. And every time the planet crosses in front of the star, you'll see another dimming. It's a very simple technique for finding planets around other stars. Luckily, we have a Spaceborne Telescope to do this, and here's the launch of the Kepler Space Telescope into a solar orbit.
1-0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Chamber pressures are building. Grounded solid motors are building in chamber pressure. Increasing at this time. Pressure's looking good. 1 second into the flight. Recovering from the initial launch transients. Passing 34 seconds. Mach 1. Vehicle's now going supersonic.
These are solid rocket boosters.
Motor chamber pressure is beginning to trail off as we're passing 45 seconds. Engine chamber pressure, good steady state value. Symmetrical burn on the groundlet solids. Coming up 55 seconds.
Anyway, the sequence going channel 1.
Standing by for burnout. Burning out of the solids. And for separation.
You see the solid rocket boosters falling off.
We have ignition of the air-lit solid motors.
We were very excited when we were on the beach in Florida near the Kennedy Space Center watching this launch. It was a fantastic day. And the nice thing is we now have a Spaceborne Telescope above the Earth's atmosphere that causes stars to twinkle and shimmer. This Spaceborne Telescope has a mirror 1 meter in diameter, has a huge field of view of 20 full moons by 20 full moons, a 95 megapixel camera, much bigger than your normal digital camera, and we can take pictures of 150,000 stars every snapshot. It's absolutely fantastic. We take a snapshot every 30 minutes, co-adding the pictures on board the spacecraft of this Spaceborne Telescope, and the mission is going to last actually at least 4 years, and we've just gotten word from NASA headquarters in Washington, D.C. that we're going to get another 2 years at least, and they've told us they may even give us yet another 2 years, for a total of 8 years of this telescope in space. So we're very excited. Today is the day that we're learning that NASA will extend the Kepler Spaceborne Telescope for another 2 years. The really great thing about this telescope is that it can measure the brightnesses of stars to within 1/100th of 1% of the brightness of a star, 1 part in 10,000. Fantastic precision. We're looking at this part of the sky. Here's the constellation Cygnus that you might know. Here's the constellation Lyra, Aquila is over here. And here's the field of view of the Kepler telescope that's taking data even as we speak right now. What Kepler does is amazing. It measures the brightnesses of stars, we call the brightness the luminous flux, over the course of time, and you're seeing a few hours here, and you can see all the white dots are the data points, and you can see that the star dimmed and then came back to full brightness. And this dimming happens over and over and over again. And in this case, the dimming is very small. You see here's 0.9995 of the average brightness, 1. So the amount of dimming is a very tiny amount, and that's what happens when an Earth-sized planet, which is very small, crosses in front of its host Sun-like star that, of course, is much larger. So we are finding Earth-sized planets, this planet being 40% larger than our own home Earth. Here's what that planet would look like. There's the little planet. You see it in silhouette because it's not illuminated on the back side, only the front side. And there's the Sun-like star, and there's the orbit around which the planet resides around that star. We then go to verify these Earth-like planets by using the world's largest telescopes on the surface of our Earth. And this is the great Keck 1 telescope located on the big island of Hawaii, high atop a hopefully dormant volcano called Mauna Kea. And you can see the telescope here. It's enormous. A person can stand right in here, and here's the aperture of the telescope. And so we measure the Doppler shift of the starlight. You remember the Doppler shift. When a race car goes by you, you hear the Doppler shift. And so even with your eyes closed, you can tell if a race car is approaching you or receding. And similarly, we use the Doppler shift of light waves from a star to tell if the star is a coming or a going, and indeed measure the speed of that star approaching or receding from us. So we gather the light from the telescope, shove it through some optics like diffraction gratings, prisms, other mirrors, and that has the effect of spreading the starlight out into all of the colors of the rainbow, of which the white light is composed: blue, green, yellow, and red. And so once we have that, we store it away on the computer, we zoom in on certain spectral lines, as we call them, and when we zoom in, we see these spectral lines Doppler shift back and forth, as the star wobbles around due to the planet. Here's the star wobbling because the planet is yanking on it gravitationally. And so we're actually seeing the reflex motion of that poor star being yanked around by that little planet that is orbiting it and pulling on it. And so it's that reflex motion of the star that we're detecting by the Doppler effect. That confirms the planet that the Kepler Spaceborne Telescope found, and tells us the mass of the planet, because of course the more mass of the planet, the more the Doppler shift will be, back and forth, the star being jerked around even more. So this is a very exciting way to confirm and measure the masses of the planets. Here's this planet I was just showing you, Kepler 10b. We think it looks something like this. It's rocky because the density of the planet is even denser than a rock, denser than the Earth. And here's a movie of what we think that rocky planet looks like. You can see the host star, a sun-like star, Kepler 10 we call it, and here is the Earth-sized planet seen dark because the front hemisphere is illuminated, the backside not. And then as you zoom in on the planet, you see that one side is illuminated. It is indeed rocky, and of course we have no idea what the geology might be on that exoplanet. The study of exogeology is going to be one of the most exciting topics in all of science in the upcoming 10, 20, 30 years as we try to understand the crustal dynamics on these planets, the volcanoes, the plate tectonics. Maybe the crust is heaving and being thrust upward by the molten rock beneath it. And so it's the study of geology on planets orbiting other stars that will be a very exciting way to compare them to our own home planet, the Earth. And maybe this is what this new planet Kepler 10b looks like. So the comparison of our own Earth to other Earth-like planets is a very profound way to understand the origins of our planet Earth and our place in the universe. Well, there's more to the story. We're finding with the Kepler Spaceborne Telescope other Earth-sized planets. Here's one we call 20F, Kepler 20F, and Kepler 20e, the size of the Earth, both of them, one of them a little smaller actually. And we've even found a star that has 6 planets crossing in front of it. You see an artist's rendering of them here. We can't actually take this picture, but we infer the existence of the planets from the dimming of the star by all 6 planets. It's quite amazing. Here's what the 6 planets look like in a sketch form relative to our solar system with the Sun, Mercury, and Venus. These 6 planets around Kepler 11 all fit inside the orbit of Venus. And here's what the system would look like if you could fly in a spaceship toward Kepler 11. You'd see the star dimming because of the 6 planets that cross in front of the star. Quite an exciting system. And of course, Kepler has found many stars that have 2, 3, 4, 5, or even 6 planets orbiting them, and here they all are, over 350 planetary systems, families of planets, whole planetary systems kin of our own solar system here around the Sun. And of course we know the time it takes each planet to go around its star, timed by the dimming as the planets cross in front, and we know where those planets are at every moment, both in the past and in the future, because we can predict where they were and where they will be. And in fact, here's a prediction of exactly where they will be. An amazing circus act of planetary systems. Just imagine how much fun it would be to study each of the planets, how those planets interact with each other. How were they born? How do they change their orbits and the architecture of each planetary system due to the gravitational interactions, the yanking of one planet on another within each system? It's quite a zoo, a menagerie of planets. We've found some exciting planets. This one, Kepler 22, is in the habitable zone with a temperature lukewarm. You could swim in the ocean on this planet and you'd be quite comfortable. So we're finding planets that have a temperature between 0 and 100 degrees Celsius, suitable for water in liquid form and hence suitable for biology as we know it. And that means that we have all the ingredients for life in the universe. If you are wondering, is it possible that there's life elsewhere beyond our own planet Earth? The answer seems clear, even though we don't have any evidence at all of life elsewhere. The logic goes something like this. The experiments for biology can be done on any planet that has lukewarm temperatures with liquid water. Certainly, the carbon-based molecules that we call organic molecules are very prevalent in the universe. We observe carbon-based molecules like methane and ethane, CO2, carbon monoxide. quite prevalently in the universe, the building blocks of amino acids and proteins of which our bodies are composed. And then, of course, liquid water, the mixer for the chemical reactions that allows the molecules to float by another molecule and combine. Water also helps them break apart and recombine into new molecules. Water is common in the universe. And of course the energy that powers biology, that powers life, is very prevalent in the universe. Energy comes in the form of stellar solar energy, tidal energy, geothermal energy, even radioactive energy. And so there are many sources of energy, and so all the ingredients of life are common in the universe. If you took a poll of molecular biologists, they would say, surely simple, primitive life must be common in our universe. How could it not be that the laws of chemistry and biology that pertain here on the Earth wouldn't occur elsewhere? But that, of course, leads to a very profound and difficult question. Is there intelligent life elsewhere in the universe, technological life? Nobody knows the answer to this question, and so I'm going to speculate as to how likely intelligent life might be. We can do a little estimate. There are something like 30 billion planetary systems within our Milky Way galaxy. The stars you see at night are all stars that are members of our Milky Way galaxy. And with 30 billion planetary systems, you might ask, what fraction of those planetary systems spawn not just life, but intelligent life? Well, the answer, of course, is we don't know. Is intelligent life a 1 in 10 throw of the biological dice, or is intelligent life a 1 in a million long shot? The answer, we don't know, but if you take the most pessimistic possibility, that intelligent life is a 1 in a million long shot, then you can see how the odds play out. With 1 in a million chances for intelligent life on 30 billion planetary systems, you can multiply 1/1,000,000th times 30 billion, and of course you get an answer in the thousands. The Milky Way galaxy must be teeming with intelligent life, with thousands of civilizations, many of which, of course, would be advanced technologically compared to us. Why advanced? Well, because they may have been born thousands or even millions of years before us, in which case they've been developing their science and their technology for thousands or millions of years longer than we have. Imagine what inventions they have, what scientific realities they've perceived, perhaps making use of sources of energy that we've never even dreamed of. So with that as the backdrop, isn't it the case that our galaxy is teeming with advanced technological civilizations? Maybe the science fiction writers were correct, that the aliens are out there flying their spaceships around, engaging in commerce and communication, maybe intergalactic poetry, perhaps occasionally some conflict, Star Wars, and perhaps they've learned to live in harmony with each other, and we, of course, could learn from them. But if this is true, that the galaxy is teeming with advanced life, why have we not found them? Why is it to this day we have no clear, definitive evidence of the advanced civilizations that are presumably filling our Milky Way galaxy? If they were wandering around in their spaceships or even robotic spacecraft, surely they would have wandered to our solar system by mere chance. But that isn't the case. So why don't we see the advanced civilizations? Where might we have gone wrong in our estimate of how common intelligent life is in our galaxy? Well, one possibility is that maybe the Earth is a rare type of planet. Yes, it's a rocky planet, there are surely many of them, but our Earth has only a small amount of water, 0.06% plus or minus of water compared to the rock of which the Earth is composed. If it were the case that our Earth had a lot less water, that water might get soaked up into the interior of the Earth, the mantle and the core, and serving as a sponge, there would be very little water on the surface of the Earth, leaving us with no water for lakes and oceans that are crucial for life. So we might have a desert world on the surface of the Earth. if there were less water. On the other hand, suppose there were twice as much water on another Earth-like planet that there is on our Earth. Well, such a planet would then be covered by water. The ocean's so thick that even Mount Everest, not to mention the continents, would be covered by water. We would live in a water world, and it's very hard to see how we would invent computers or rocket ships in a world completely covered by water, where electrical circuits would short out. So it's an interesting question as to whether our planet Earth has a special composition, especially the water, making life here and intelligent life possible. Another interesting aspect of intelligent life is that it requires Darwinian evolution for life to evolve from primitive species to advanced species with big brains. Is it true that evolution always leads to smarter and smarter and smarter species? Well, we can answer this question by looking no farther than to the fossil record of the dinosaurs. The dinosaurs roamed the Earth for 200 million years, and yet, as you know, during those 200 million years, the dinosaurs' brains did not get larger. They were not very bright. They had brains the size of walnuts. They were no smarter than chickens. And so dinosaurs offer a suggestion that over the course of generations, hundreds of generations, thousands of generations, the high IQ dinosaurs didn't systematically and preferentially pass along their genes to their next of kin, to their children, and to the following generations. Intelligence is not necessarily a dominant trait that allows you to survive against the elements and pass on your genes to the next generation. Maybe we humans are some sort of a twig on the evolutionary tree with our advanced brains. And then finally, maybe life is rare in the galaxy because, yes, it springs forth, but one advanced technological civilization develops such good technology that they can build weapons, enormous, powerful, and frightening weapons that can actually threaten global survival of the species. Also, maybe advanced technological species develop the technological ability to threaten their own environment, the cocoon of ecosystems that make life possible. We humans, of course, are dealing with both challenges, weapons that are very powerful and the ability to harm our own Earth's environment. Perhaps the lack of aliens in the galaxy is telling us something about the severe challenge of surviving one's own capabilities. So I will finish by saying that a great challenge for us humans is to use radio telescopes and regular optical telescopes to hunt for the signals, whether they're radio waves or laser beams coming from advanced civilizations, to find out if they are in fact out there. Maybe we'll learn where to point our radio telescopes to pick up the radio and television transmissions from any advanced species out there. And we can use the Kepler Earth-sized planets to point our radio telescopes at those potential habitable worlds. So we live in an amazing era when we are indeed searching for planets, Earth-like planets, and I think it's quite exciting to realize that we've made some progress as a young species ourselves. We're finding the first Earth-sized planets. We're using the Keck telescope on Hawaii to prove that those planets are rocky, like the Earth. We are finding that Earth-sized planets are extremely common. There are millions or billions of them within our Milky Way galaxy. And surely, life at the primitive stages must be common, because the chemical reactions must occur frequently whenever you have liquid water and carbon-based molecules mixing together. But intelligent technological life might be more rare than the science fiction writers and the science fiction films have implied. Perhaps this is telling us that we should take care of our home planet Earth. It may well be a more precious planet than we had ever imagined. And I think I will stop there. Thank you, Zoe, for inviting me to give this talk.